Hi, my name is Paul Davis. Thank you for giving me the opportunity to present to you my Intelligent Interactive Surface, a low-cost, tangible 3D interface for improved spatial memory utilization. The purpose of my research was to create a low-cost, scalable, tangible user interface that may facilitate 3D modeling with voxels. The idea was incepted after the influx of new computer users that came with the arrival of COVID-19. There is a crippling lack of intuitiveness to many of our user interfaces that less computer literate populations struggle with. With no complicated buttons or menu navigation, my system aims to give users the ability to move virtual objects with their hands. Let's first examine the shortcomings of currently available technologies. Traditional force sensing resistors have difficulty sensing static forces and are expensive at about $10 per unit. That cost is exponential for array building. Computer vision would be an excellent solution if depth sensing cameras were affordable for the common user. To create my force sensing matrix, I used a cheap piezo-resistive electronic packaging material called Velostat. Because of the material's piezo-resistive properties, electrical resistance is reduced by the application of mechanical force. Let's take a look at Figure 1. Here you could see where we create a sandwich sensor by arranging copper tape into columns for the bottom layer, rows for the top layer, and placing a Velostat sheet in the middle. Each row is wired into a voltage divider circuit using a 1000 ohm pull-down resistor. By applying voltage to one column at a time, we can determine the location and magnitude of forces applied to the array. Next, we visualize the analog readings in 2D to observe the activity of each sensor across the array. The visual results may be seen in Figure 3. The left figure is the result after placing a single wooden block in the center of the array. As you can see, there is significant crosstalk between the sensors in the middle row. The figure on the right shows the results after redesigning the sensor, which I will discuss more shortly. Because the analog readings by the microcontroller yield arbitrary values, I used the formula for voltage drop across a voltage divider circuit to derive the following equation, which yields the electrical resistance of the Velostat in ohms. The Velostat resistance for 3 fixed resistor values can be seen in Figure 5. As you can see, the graphs aren't linear, which is largely due to deformation of the Velostat material. This presents a challenge for variable force detection. We next attempt to produce more linear readings by measuring capacitance instead. I created a new circuit that introduced a capacitor to each voltage divider, which can be seen in Figure 2. Although the force capacitance graph was much more linear, it must be considered that capacitance is measured by observing the time it takes to charge the capacitor. As matrix size increases, this becomes impractical due to extended charge and discharge time, unless each node is equipped with its own capacitor, which leads to an undesirable increase in hardware cost and complexity. To deal with crosstalk, an algorithm was devised to isolate processing to the node with the highest net change in resistance per cycle. Additional issues that were resolved using software include accidental touches, taps, or vibrations. This was accomplished by sampling each node multiple times and discarding samples that contained any outliers. Pictured on the left is the final model, which is like the first resistance-based model, except that the sensor nodes are further apart and the Velostat is cut into squares that are placed over each node. Pictured on the right is the corresponding 3D model that my software displayed in real time by receiving serial data from the Arduino. The sensor was deemed successful after multiple trials showed an accurate 3D representation of the constructed model. The 3D visualization software was written in Python and generates the navigable environment using OpenGL. This software will be important for the next stage of my research, which involves direct observation of a sample of users using both a point-and-click user interface and the tangible user interface. Metrics for evaluation will include time to learn, the interface, speed of model completion, rate of error, subjective satisfaction, and ability to recall previously built models without a reference. In closing, I would like to thank the UHD Scholars Academy for giving me the opportunity to speak before you today, Dr. Ting Zhang for providing mentorship and guidance, and Kasi for ensuring fair opportunities for all of us. Thank you.